Okay, so it is my pleasure to introduce our speaker of today is Pietro Benetti Genolini, who studied physics in Milan with me in license level, and then went to the UK and got his master at Cambridge University. He then got his PhD at Oxford University and had postdoctoral positions in Cambridge University and now at King's College in London. So today, Pietro will talk about localization of the action in anti-de Sitter conformal field theory correspondence. So please, Pietro, take the lead.
Thank you. Thank you very much for the invitation, Matteo, and everyone else, of course. And so I looked at the previous instances of these seminars briefly, and I decided to give a much simpler talk than some of the previous instances. And I hope that I'm not going too low with the level, but if you have questions, please do stop me at any time and I'll be happy to go deeper if needed. So this is work that I've been doing with some people in Oxford and King's over the past couple of years. And it's a long project in the area of the AdS CFT correspondence. So rather than going straight into the deep end, I thought I would start with a few observations on a simple metric. So starting with math rather than the physics. So first of all, a word of caution, I will always be in Euclidean signature. So this is a metric for what would be a black hole in Lorentzian signature. You see that it's a four-dimensional metric. G sigma G is the metric on a Riemann surface of genus G. And then it depends on a function V, and it also contains a U1 gauge connection, a U1 gauge field with curvature given by F in this way. So these are, for any Q, these are solutions of a theory that is called Einstein-Maxwell with a negative cosmological constant. So you see that it's Einstein because it contains the Einstein-Hilbert action, which is just the Ricci scalar curvature. It's Maxwell because it contains the kinetic term for a Maxwell field, which is F squared, the curvature squared. And it has a negative cosmological constant because it contains a constant term, which is the cosmological constant. So these are solutions that are regular for any radius r larger than the largest root of v, because when v vanishes, then you have the divergence in the metric. However, you can see that as you go closer to the point where v vanishes, if you change coordinates appropriately, you see that actually the space closes off smoothly. So the topology of this solution is R2, which is described by this. It's it's not metrically R2. It's like a cigar kind of, times sigma G without any fibration. So it's a very simple metric, and this is going to be the paradigm of everything that happens afterwards. So, however, let's look at the boundary of this metric. So if you take the radial coordinate to infinity, v scales like r squared. This becomes the dominant term, and therefore the metric looks like this. So there is a dr divided by r squared times an overall r squared that multiplies a product metric. These type of metrics that look like this, for which I can define a conformal boundary and such that the metric splits like this, is called asymptotically locally hyperbolic. It's just a name for the time's sake. Should I look at the chart or can? So I've used I've used, I've set lambda is equal to -3. It's just a conventional choice. I can reinsert lambda, but it's just a unit of measure. Okay, so this is the structure of the metric. So it kind of closes off smoothly. It has an R2 times sigma G, and at infinity there is a conformal boundary where the metric looks like just a product of S1 times sigma G, where the S1 is given by tau, is parameterized by tau. Okay, so now let's look at something peculiar that happens for this metric. There is an obvious killing vector. There is an obvious isometry, which is just the shift of tau, because nothing depends on tau in the space. So d tau is a killing vector. There are many more killing vectors, but d tau is definitely a killing vector. And its norm is equal to VR, right? Because that's just the norm of d tau. And because we're in Euclidean, the norm is positive unless it's zero. Sorry, a vector vanishes if and only if its norm vanishes. And in norm is positive everywhere, apart from R is equal to R0, where we closed off our space. So d tau is a fixed point set that is isomorphic to sigma G at R is equal to R0, to R0, okay? So now let's compute the action of this solution. So when I say compute the action, I mean that we substitute into S the values of R and F for this solution, and I compute what it is. It will be divergent, but there is a standard method to regularize this. And you find that it's just pi over 2g times 1 minus g. But 1 minus g you recognize as the Euler characteristic of the Riemann surface. So in a sense, the on-shell action for this solution, which a priori depends on the metric, because as I showed you, the action depends explicitly on the metric in the Ricci, in the volume. It also depends on the gauge bundle. All these data are forgotten, are erased, and at the end, you only find something that depends on the topology of the space, because the Euler character is just topological invariant. Okay, so the question that we would like to ask is this a generic feature? Is there something that says that for many other solutions, the on-shell action is just topological invariant? Okay, so this is the question that we ask.
Sorry, I have a question.
Yes. Yeah.
The on-shell, you put the metric, gauge field, and rigid scalar, but you use the asymptotic metric or just near horizon metric?
I use the metric on the full space, so literally this.
Okay, for generic metric, not asymptotic or not near horizon metric. By the way, second question is the near horizon metric is also the solution of this the same theory, Einstein-Maxwell theory.
Yes. So this metric, yes. So this metric has two limiting behavior. So there are two limiting behavior. I can either set R that sends to infinity, and I obtain this effective metric near the boundary, or I can set R that goes to R0, and I obtain the metric on R2 times sigma G here. So both solutions, so both near horizon and conformal boundary, are also solutions of the Einstein-Maxwell theory with the appropriate limit of the F. However, when I say that I compute the on-shell action, I am using the globally defined metric. So I'm using not just the limiting behaviors. I'm using literally the function on the entire space-time.
Thank you very much, sir.
Okay. Okay, so let me go on. So why do we look at asymptotically locally hyperbolic? is because of the AdS CFT correspondence. So the AdS CFT correspondence is one of the great breakthrough of string theory. And it says that there is a description of quantum gravity in certain spaces that is given purely in terms of a quantum field theory. So in particular, it says that if you have an asymptotically locally hyperbolic space, so if you have an asymptotically locally AdS space in Lorentzian, and you consider quantum gravity on it, this will be equal to the field theory on a space that is conformal to the boundary. So all asymptotically locally hyperbolic spaces have a boundary, and you can consider a quantum field theory on the boundary. This is a great breakthrough because it relates quantum gravity, of which we know nothing, to quantum field theory, of which we say that we know a lot about. And it can be made more precise. So more precisely, it says that in the computationally sensible limit, which is a large degrees of freedom limit, in a sense, it says that the partition function of a conformal field theory on a space MD with a metric G is equal to this e to the minus I. So the free energy of the theory is equal to the on-shell action of gravity on a space Y d+1 such that the conformal boundary of Y is equal to M, and the metric on Y is an asymptotically locally hyperbolic with this behavior. So there is a coordinate Z such that this holds. You can insert a coordinate near a neighborhood of the conformal boundary such that this holds. And to connect with the previous expression, you just set Z is equal to 1 over R, and you see that this becomes dr squared divided by R squared plus R squared G, right? So the previous one is an asymptotically locally hyperbolic metric. I just used a different coordinates. Okay, however, this prescription, which seems very, very precise, is actually not very precise, right? Because I have not told you, there are mathematicians in the audience, and you surely know much better than I, that I should have given you what does it mean to have a sum here? What is the domain of this sum? This sum arises because I'm doing a semi-classical expansion, so a saddle point approximation to the quantum gravity path integral, which is something that I don't really know how to do, but I claim that in the semi-classical approximation, I obtain classical gravity. And a priori, I could have multiple saddle points for this path integral, and this is the domain of the sum. So moreover, we are interested in trying to learn something about the domain of the sum in this AdS CFT prescription. And also we would like to find whether there is some geometry inserted in the on-shell action. Can it be expressed in terms of something that depends on the topology or the geometry of Y? And can it be simplified in the same way that for the previous example, I could simplify everything about the on-shell action and just find something that depends on the topology of a factor of the space. Okay, so this is the idea, and in order to do
just
this,
a quick question. Yes. So the domain is finite or infinite? So
that's a very good question. We have no idea. So in all the known cases, in the cases where you can do this equality and check it explicitly, in the semi-classical approximation, there is usually one saddle point that contributes at the leading term. However, I'm going to show you at the very end that that you can find cases where there are two complex saddle points, so for which the I is complex, and they have the same leading real term, but they differ by a phases. So a priori, you expect many complex saddle points, because if I give you an integral, even if it's real, and I tell you to do a saddle point approximation, it may have complex saddle points, and it may have infinite or finite contributing. However, let's say that physics limits your your possibilities in the sense that you expect that if you have a very simple geometry at the boundary, you don't expect, you know, bubbles in the interior. You expect that if you have a sphere, the leading behavior probably is given by the ball filling the sphere. I mean, yes, you could do you know, blow-ups of the singularity at the origin and obtain something more complex, but probably the ball should be your first guess. So in this sense, yeah. Okay. So because I don't know quantum gravity, and nor I think nobody does, I'm gonna study a much simpler theory. I'm gonna start with an effective theory in 4 dimensions, which is minimal supergravity in 4 dimensions. So the simplest supergravity, and I'm gonna use super because if I have supersymmetry, I have more control over the computations, as I'm gonna show you. The bosonic sector of this theory, I'm going to set the fermionic sector to 0. So there will be almost no fermions apart in this slide. And the bosonic sector is just Einstein-Maxwell theory with a cosmological constant. So this is literally the okay, it's not the simplest. The simplest would be just Einstein, but this is the next to simple theory that you can find in a textbook in GR. So a solution of this theory is supersymmetric. So we say that a solution of the supergravity theory is supersymmetric if there exists a spinor on the spacetime, so a Dirac spinor epsilon that satisfies this generalized killing spinor equation. So there is a differential operator that includes the U1 connection and the F, the curvature. Gamma are the generators of the Clifford algebra. And if you have a spinor that satisfies this equation, then your solution is supersymmetric. And we will only consider supersymmetric solutions to this supergravity. So these are spacetimes with a metric and a U1 gauge bundle that satisfy the equations of motion coming from this. So the Maxwell equation and the Einstein equation coming from this. And in addition, they also have a spinor bundle, and they also have a spin bundle with a section epsilon that satisfies this equation. If you have this structure, you can construct things out of the spinors. Is a standard construction in spinor geometry. And one of the first things that you find is that you can construct this vector, which is a bilinear in the spinor, is constructed out of the Hermitian conjugate of the spinor, gamma mu, gamma 5, which is the product of all the gammas, times the spinor itself. And you can show using this equation that this vector is killing. So it generates an isometry. This means that all the supersymmetric solutions to this theory have a U1 isometry. Okay, that's locally. Globally, I'm assuming that the orbits close. If the orbits don't close, there is a way of dealing with that, but I'm simplifying for the sake of the talk. Okay. So now let me do a small detour, and then I'll go back to the main thread of the talk.
May I ask
if you have
yes. Case? I'm sorry.
Yes, of course.
As I understand, this is a covariant derivative of epsilon, which is some spinor parameter. It's somehow variation of, for instance, if I have some size spinor, if I take the variation of this spinor, it's proportional to covariant derivative of d epsilon, right? If I take this epsilon as a supersymmetric parameter. So
yes. Yeah.
It is somehow fixing a gauge in this sense. I mean, if I take variation of G mu is 0.
No, so the way it arises is the following. Okay, so small detour into supergravity. A supergravity theory contains a set of bosonic fields and a set of fermionic fields. This is generically, right? So, and they are supersymmetric. The action or the theory is supersymmetric if you have a set of bosonic variations and a set of fermionic variations, such that the action is invariant under these. So the bosonic variation will contain the fermions, and the fermionic variations will contain the bosons. This is just a property of any supersymmetric theory. So, you know, like the simplest case would be the chiral spinor is something of this sort, or and so on, right? So now, when I consider supersymmetric solutions, supersymmetric classical solutions, it means that I set the fermionic fields to 0. When I set the fermionic fields to 0, this implies from these that the bosons don't vary under supersymmetry. So the solution is obviously supersymmetric, provided that these fermionic variations are just vanishing. Because if they are not vanishing, that means that it's not consistent to set the fermions to 0, because then when I do the supersymmetry variations, I would obtain something that takes me out of 0, right? So these type of generalized killing spinors are the fermionic variations. So in fact, this supersymmetric killing spinor is the variation of what is called the gravitino. So it's not so much a choice of gauge, but it's a choice of a set of solutions of the theory that preserve supersymmetry in a very particular way, which is by setting the fermions to 0. Does this answer the question?
Thank you very much for very clear answer. Thank you very much.
Okay, thank you for the question. Okay, so now let me do a detour into isometries. In general, as our friends geometers know very well, the fixed point sets of any isometry have even codimensions. This means that in 4 dimensions, they can only be 4-dimensional, 2-dimensional, or 0-dimensional. If it's 4-dimensional, it means that the entire space-time is invariant under the isometry. That's very great. That's great, but it's a trivial isometry, so we are not going to consider that. More interestingly, the fixed point sets of an isometry can be 0-dimensional or 2-dimensional. If it's a 0-dimensional fixed point set, it's usually called a nut in physics. So near a nut, you can write the metric as just the metric on the flat space. This is a triviality. Near any point, a manifold looks like flat space. And the killing vector near the nut, in a neighborhood of the nut, can be written as the vector that rotates R2 times R2, the 2 transverse planes, with some weights B1 and B2. If instead I have a 2-dimensional fixed point set, this is called a bolt. And if I have a bolt, then I can write the metric near the bolt as the transverse space times the metric on the bolt. And again, the killing vector, because it doesn't rotate the bolt, that's the definition, it rotates the transverse space. It rotates the orthogonal R near the bolt, which is this, which is why it's this. Omega is just a generic form that appears in a fibration. Okay, so these are the 2 fixed point sets. Let me give you an example. Back to the black holes. As we said, d tau as a fixed point set that is identical to sigma g. I've written the metric in an explicit set of coordinates. So we say that it has a bolt on sigma g. Whereas if I add d tau plus d phi, where d phi is the metric is a coordinate on the Riemann surface, this will have a nut at theta is equal to 0 on the bolt. Okay, on the bolt of the previous vector. Okay, so you can find killing vectors that have on the same space that have killing the bolts and nuts and so on. Okay, so given that you now know everything that is needed, let me give you the physics. So we showed that the on-shell action for any smooth supersymmetric solution to the supergravity that we were finding, which is just Einstein-Maxwell with a cosmological constant, can be expressed in terms of topological data at the fixed point sets of the killing vector constructed out of the killing spinor. Remember that any supersymmetric solution has a killing vector, so it has an isometry, and it may have fixed points. And these fixed points are either zero-dimensional, so they are characterized by their weights, B1 and B2, or they are two-dimensional, in which case they are surfaces, and being surfaces, they have a tangent bundle and a normal bundle. And you can show that the on-shell action is just expressed in terms of either a combination of the weights at the fixed point, or as a combination of the C1 and of the Chern classes of the tangent and normal bundle to the bolts. Okay, so in fact here you immediately see, well, okay, let me skip the proof, and if you need, I can come back later because I wanted to give you some physics. So let me give you an example rather than a proof. An example is worth 1,000 words. So let's consider AdS4. AdS4 is the simplest asymptotically, in fact, it's not just asymptotically hyperbolic, locally hyperbolic, it's literally hyperbolic space. And it has this metric. It's valid, these are the metric in global coordinates, so it's valid everywhere on space-time. There is a killing vector, Xi, which is d phi 1 plus or minus, meaning that there are two killing vectors. These are the vectors that rotate. If you had written, if you like geometry, the geometrical viewpoint, this is a metric. This is a metric on S3, and S3 you can write as a Hopf vibration, right? As an S2, as a vibration over S. Sorry. Is a vibration over S2. Is a vibration over S2. And this killing vector is the Hopf fiber killing vector. Is the killing vector that rotates the S1. Okay, anyway, forget about it. So this killing vector, the norm of this killing vector is just R squared. It's a trivial computation. Therefore, in both cases, they have a nut at R is equal to 0. At a fixed point set, so if the killing vector vanishes, the spinor that was used to construct the killing vector must become chiral. Therefore, there is an additional label that is given to the vector, to this fixed point sets, which is the chirality of the spinor there. It's a plus or a minus. And you can show that if you choose the plus side, the plus sign here, then your spinor will have negative chirality. And if you choose the minus sign, then your spinor will have positive chirality, and so on, okay? Now I just apply the formula, and I find that, well, you just substitute B1 and B2 inside the formula, and you find that in both cases, the action is pi over 2g. This is sensible because it doesn't depend on the choice of supersymmetric structure. It doesn't depend on the choice of spinor, because I had two different spinors that gave me two different killing vectors, but the space was the same. So it makes sense that it didn't change, okay? However, AdS4 is very particular because I can also include, so it's a solution to the Einstein equation with zero gauge field, but it's also a solution of the Einstein equation if you add a gauge field. In particular, you can add an abelian instanton, so something that satisfies F is equal to star F. The supersymmetric structure is different because the the killing vector, the killing equation is different, and the killing vector formulated out of that supersymmetric structure has this form. And you can show that in this case, it has still a knot at r is equal to 0, but in that case, the action is different. Okay, so the action depends also, it depends on G and on the metric and the gauge field, but it's always formulated in terms of simple topological data at the fixed points. Okay, this is particularly nice. Let's go to our old friends, the black holes. Again, you have this metric. Remember that the killing vector field d tau had a bold isomorphic to sigma g. I didn't choose the killing vector randomly. That was the supersymmetric killing vector, meaning the killing vector constructed out of the supersymmetry. And it only exists if G is larger than 1. And what you find is that indeed there is no normal bundle because it's a trivial fibration. As I showed you, it's R2 times sigma G. And it's just the C1, but that is the Euler character, right? That's exactly what I showed you earlier. So it's 1/2 times the Euler character, which is the integral of C1. This is particularly nice because it allows us to compute the on-shell action of all the solutions for any Q. It doesn't depend on Q. This is sensible because there is a family of solutions that depends on Q smoothly. But for Q is equal to 0, the topology of the space changes, and it's not anymore an R2 that capses off. It's not a disk anymore. Instead, it develops an infinite throat. So it becomes a cylinder of sort. However, because the action doesn't depend on Q, the action of that case is the same as this one. This is particularly important because the Q is equal to 0 case is the extremal black hole, and extremal black holes are particularly nice for various physical reasons. Okay, let me forget about the entropy. So we can also consider solutions that are more complicated than until now I've only considered trivial topologies. Either they were the flat space, like AdS4 is just flat space topology, or they were a product topology of a disk times a Riemann surface. However, I can consider topologies that, as Ayman was saying earlier, they are more complicated. They are blow-ups of the origin, or they are various fiber bundles, such as, products of the canonical bundle over any sigma G. The boundary of this space is S3 modded by ZP. It's just a property of this, here I'm talking about the total space of the fiber bundle. And there is a non-trivial gauge field that supports this construction with a flux through sigma. These are supersymmetric solutions. You don't need to know the metric in order to compute the action, because I know that the SUSY killing vector will rotate the fiber, rotate the S1 fiber of this space. And indeed, because I know that it's just the rotation of the fiber, the supersymmetric killing vector, I know that the fixed point sets will be the base of the base of the bundle, which is isomorphic to sigma G. And in this case, I already know what is the normal bundle. The normal bundle is literally O minus P. So I can compute the on-shell action without any knowledge of the metric. It's literally the Euler character plus or minus the P. Okay. So it's particularly nice because it allows us to actually do peak, to have a peak at the domain of the sum, in the sense that I can now give a more concrete and computational foundation to the statement that I was making earlier, that the simplest topology dominates the saddle point. it's true, because if I do a blow up, I can show that the action increases. And if the action increases, because it appears in the saddle point as e to the minus I, it will be a subleading contribution. It's only the lowest action that it's leading. Okay, so in this sense, this gives us control over that domain of the sum. However, there are at least two different trajectories that we can take out of this. So before I go on, any questions about what I said until now?
If you can just explain the simplification from the integral to the second line. So,
yes. So, okay. So that. Okay. So, do you agree that that this killing vector, so the killing vector that rotates the fiber of this bundle, so this bundle has a fiber that is like it's a U1, and then there is the radial coordinate as well. So it's like an R fiber. So it's the fiber is C, right? But in C there will be there is a radial coordinate, and then there is an angular coordinate, right? So the killing vector, the radial coordinate corresponds to the coordinate that becomes the asymptotically hyperbolic at infinity. It's the thing that allows us to write the conformal boundary. And then there will be a coordinate that is glued to the sigma g at the boundary, and that corresponds to rotation in each complex plane fiber. So the killing vector, it's an isometry of the metric. This is non-trivial, but once you show that the SUSY killing vector is deep psi, is this, then it's trivially an isometry, because we showed that the killing vector constructed out of the supersymmetry, the vector constructed out of the supersymmetry is killing. So this is the angular, and the fixed point set of this vector, of the vector that rotates the plane, is by construction is the base of the bundle.
Mm-hmm.
Right? It's the thing that is left untouched by this
yes.
By this rotation. Great. So these are the bolts. The bolt for this killing vector is the base of the bundle.
Okay.
So there is no nut, it's just a bolt. So I can go back to the formula, and I have this part of the formula that I need to consider. Now, C1 of T sigma, the tangent bundle to sigma g, so C1 of T sigma g is literally the Euler character of the Riemann surface, which is, so the integral of C1 is equal to chi, which is equal to 2 minus 2g. Because there is a 1/2 in front, this becomes 1 minus g.
Okay.
Then there is a non-trivial part. So then I have this part. So the integral of C1 of n sigma, so the normal bundle, it's by definition P. It's literally when I split it, it becomes P. The non-trivial part is showing that the signs of the chirality of the spinor is such that this plus minus is related to this plus minus. It's whatever. That's the non-trivial part for which you have to sit down and do a computation.
Okay.
But apart from that, is it more clear? Is it clear?
Yes. Thank you very much. Yes.
Great. Cool.
One more question.
Yeah.
Sorry, by the way.
Please.
It is quite technical, but I have a very stupid question. Maybe it's really a stupid question. As I understand, by using this supersymmetry, we can construct, we can actually calculate on-shell action by this topological invariance or topological terms. But
yes,
the question is, my question is, how can I know whether this space-time contains a black hole or not? I mean, in the on-shell action, as I understand, the empty space time, for instance, AdS space and AdS black hole, they have, as I understand, they have different type of on-shell action. So how can I say we have a thermal object, we have a black hole or just empty space, but just action?
Yes, so you wouldn't just be able to do it from the on-shell action. You would need something more. So the on-shell action allows you to compare with the field theory. However, because it's related to the field theory partition function. However, saying whether it's a thermal, it's a more non-trivial thing to check. Well, there are necessary conditions to have a black hole. For instance, as you said, you need to have a thermal object, which means that you need to have a circle. So for instance, something that at the boundary is just a 3-sphere will not be a black hole, will not be filled by a black hole, because a black hole always has a cigar geometry in Euclidean, always has an S1. So can I go back to this question at the end?
Of course.
It's a very interesting question, but let me go back to it. Okay, so let me tell you at least about one direction that is particularly interesting, I think. So as I told you, we're doing approximations of quantum gravity. So when you do an approximation, you work with an effective theory, and effective theory consists of an expansion in derivatives. The minimal theory that I worked with until now contains 2 derivatives. The Ricci scalar contains 2 derivatives of the metric, and F squared contains 2 derivatives of the gauge field. However, there are a priori higher derivative corrections. It's really hard to find what are the higher derivative corrections to a theory. A priori, you just write all the terms, down all the terms, but then you need something in order to say this appears, this doesn't appear. And these people, Nikolai Bovev, Anthony Charles, Kirill Ristov, and Valentin Rice, have proposed a form of the 4 derivative corrections to the minimal gauge supergravity. So it's formed of two actions. One is a supersymmetrization of the Weil square term. So it starts with Weil tensor squared, and then it's supersymmetrized in the sense that it's invariant on the supersymmetry transformation. So it contains F squared, it contains F to the 4th, it contains R times F squared, it contains various terms. And then you have the Gauss-Bonnet term. So the Gauss-Bonnet term in 4 dimensions. So in 2 dimensions, the Gauss-Bonnet term is just the Ricci scalar, because the curvature is just the integral of the curvature is the Euler character. In 4 dimensions, the Gauss-Bonnet term is not the Ricci, it's a Riemann. It's Riemann squared minus 4 Ricci squared plus R squared, I think, with an overall factor in front. But whatever, the important bit is that this is the form that they propose. Then you sit down and you think, does the localization property, so this idea that the on-shell action is only given by topological data, apply also to the higher derivative terms? And the proof goes in 2 steps. So first, you realize, and this is a very highly non-trivial step, that the solutions to the two derivative equations of motion, just Einstein and Maxwell, are also solution of the 4 derivative equations of motion. A priori, there is no reason this should be true. If I give you an effective expansion and I tell you, the minimums, the solutions to the lowest order are also solution to the higher order, generically, it's not true. In fact, we know that it's not true in higher dimensions. However, it's true in this case. Moreover, by construction of Bobev et al., the supersymmetry condition for the 4-derivative action is the same as the 2-derivative action. Therefore, any any solution to the 2-derivative, any supersymmetric solution to the 2-derivative equations of motion is a supersymmetric solution to the 4-derivative equations of motion. In fact, because the supersymmetry is the same, all the supersymmetric solution to the 4-derivative equations of motion are the supersymmetric solution to the 2-derivative equations of motion, right? Therefore, you have this structure. So the solution to the 4-derivative equations of motion strictly contain the 2-derivative solutions, which strictly contains the supersymmetric solutions. Okay, great. It could have been something different. It could have been 4-derivative with 2-derivative in this way, and the supersymmetric solution to the 2-derivative and the supersymmetric solution to the 4-derivative. It could have been something very different. Instead, it just so happens that for this theory, it's like this. However, this is crucial because in this case, I can literally do the proof that I've not showed you, but that exists of the 2-derivative equations of action, and I can go through the step. And what I find is that the 4-derivative equation on shell action also localizes, in the sense that I can write the 4-derivative action as the sum of the 2-derivative on shell action plus contributions from the nuts and contributions from the bolts, where alpha 1 and alpha 2 are the coefficients that were introduced earlier. Notice that it's lower order in the derivatives because it doesn't contain the divided by g, right? There is no divided by g. So when g goes to 0, which is the same as doing the lowest order in the effective field theory, the leading term will dominate, and this will be just a finite piece, okay? And then a priori, there is a 6th derivative correction that starts with g, that is multiplied by g, and so on, okay? And this shows the same localization properties, where by localization properties, I mean that it looks like the result of a localization theorem in geometry. If you think about Berlin-Werner, the equivariant localization theorem, the index theorems, fixed point theorems, that say that if you have an action of a group on a manifold and you do an integral that is equivariant with respect to this group action, then the integral only receives contributions from the fixed point sets of this action. These are very beautiful, in my opinion, very beautiful theorems of the 20th century geometry, like Thiabout, Berlin-Werner, Deusermann-Ekman, and this is in the same spirit. Okay, so in the interest of time, let me give you just a very quick idea about what the next step would be, which is the comparison to the field theory. So I showed you this formula, and now we have studied in a lot of depth, in 1 hour of depth, this side of the correspondence. I've not mentioned until now this side of the correspondence. I've told you, this is dual to a CFT on a manifold. I've not told you which CFT I should be using. There are many conformal field theories. I've only told you that the conformal manifold is that the manifold is supposed to be at the isomorphic to the conformal boundary of the asymptotically locally hyperbolic, but I've not told you how to put supersymmetric theories on it and whatever. I did it consciously. So I'm only going to tell you about which field theory you should put. So the way you choose the field theory to compare to is by actually embedding in quantum gravity. So our best and only probably only theory of quantum gravity, is string theory, or in this case, M theory. And we look at the low energy description of M theory, which is 11-dimensional supergravity. And we look at solutions of 11-dimensional supergravity that have a product or fiber product structure into a four-dimensional space and a 7-dimensional space. In particular, we look for solutions that allow for consistent truncation. This means that when I take the 11-dimensional, take the ansatz, reduce the 11-dimensional in equations of motion Kaluza-Klein style on the 7-dimensional space, what you find are 4-dimensional equations of motion that only depends on 4-dimensional degrees of freedom. And if they are self-consistent, meaning that when I find a solution of them, I can always then do the procedure backwards, then I say that I have a consistent truncation. If you're familiar with the very old original Kaluza-Klein reduction, that's not a consistent truncation because there is a scalar, and that scalar is not consistent, does not allow you for a consistent truncation. That scalar appears as a source of the 4-dimensional degrees of freedom. Therefore, it's not consistent to set it to 0 because it sources itself. So given such a consistent truncation, the field theory is defined by a choice of X7. Okay, so if you give me a 7-dimensional space that allows you to consistent truncation, then I tell you, this field theory, this 7-manifold corresponds to this field theory, and so on. Then the idea is that you compute the partition function of that field theory on a 3-dimensional manifold. You take the large n limit and you compare with gravity. Okay, so there is one, I'm going to skip over most of this, but there is one consistent truncation that is done on a special class of 7-dimensional manifolds that are called Sasaki-Einstein. The sphere is the Sasaki-Einstein paradigmatic example, and it corresponds to some field theory. Ignore this. And you can compute the partition function for many of these field theories, and you obtain something that you can compare with gravity, and it works. And the match works. Okay. However, there is a more interesting field theory. This field theory arises from a different 7-dimensional manifold that is not Sasaki-Einstein, which has this form. Is a fiber product of an hyperbolic manifold, an hyperbolic 3 manifold, times the 4-sphere. These field theories arise from a very mysterious 6-dimensional superconformal field theory wrapped on the hyperbolic manifold. There is a whole study of this field theory. It's one of the big mysteries in theoretical physics. What are the degrees of freedom of this field theory? What happens when I compactify on spaces of different dimensions? But in particular, if you compactify this field theory on an hyperbolic space, because you go from 6 to -3, you go to a 3-dimensional superconformal field theory, which is the thing that I was studying, of which I was studying the gravitational duals. So when you do the consistent truncation from 11 dimension on this 7-dimensional space, you don't just get minimal gauge supergravity. Instead, you obtain minimal gauge supergravity plus a theta term. This theta term you can always add to a 4-dimensional theory. And it arises from a topological term that exists in 11-dimensional supergravity. Not important.
By the way, if I do Kaluza-Klein, for instance, in 11 dimension, the X7, there's a necessary condition. It should be compact or not? I mean,
it doesn't have to be compact. It needs to have finite volume.
okay.
Yeah.
So that's why you choose this AdS 5 or AdS, as I remember from previous.
No. So this is why I choose S4, like sigma 3 times the X7 has to be compact.
Okay, it is not.
This is the internal space So it's X7. So X7 is, in the cases that I've showed you, is SE7 or sigma 3 times S4.
Okay. The S4 part is compact, but epsilon.
So this is compact. This I'm assuming is compact. This can also be non-compact, but that's just a property of hyperbolic manifolds, which can be non-compact but have finite volumes.
Thank you very much.
These are called cusped manifolds. Anyway, the important bit is that when I do the Wick rotation, when I go to Euclidean, the action becomes complex necessarily because of the theta term. This is always the case in 4-dimension. And if I do the same method that I was using earlier in order to prove the localization of the action, I find that the theta dependence factorizes in front with this particular combination. It's a strange fact of life, but it's explained by physics. It's in some sense, because when I do the embedding of the 4-dimensional theory in 11-dimensional supergravity, the embedding of the two gives me a dictionary between the 4-dimensional objects and the 11-dimensional objects. This dictionary is this, right? It tells me that the 4-dimensional gravitational constant is related to the volume of the hyperbolic manifold, whereas the theta term, the theta angle, is related to the gravitational Chern-Simons on the hyperbolic manifold. Well, this is the gravitational Chern-Simons. This particular combination, pi divided by 2 plus or minus I theta, is not a random combination. It's actually a natural topological invariance of hyperbolic manifolds that is called the complex hyperbolic volume. So I thought I would talk about this because it's particularly cute and it's geometric, and perhaps the mathematicians would like it. But this is it's a complex hyperbolic volume, and it had been studied since the 80s. And this is consistent with everything we know from physics, because this mysterious 6-dimensional conformal field theory, when it's compactified on an hyperbolic manifold, it's supposed to give you a 3-dimensional field theory that only depends on the topology of the hyperbolic manifold that you have compactified on. And this is consistent because indeed you find something that is a topological invariant. It's weird that it's topological because there is a volume, but it's called, there is a theorem that says that the volume is topological for hyperbolic manifolds. So I'll conclude with this case. So let's go back to the SUSY black hole. The SUSY black hole, which is your favorite metric by now, the on-shell action of the SUSY black hole with the theta angle added gives, if Q is larger than 0, gives the complex hyperbolic volume multiplied by 1 minus G. And if Q is less than 0, if the charge is less than 0, gives the complex conjugate of the complex hyperbolic volume. Therefore, you expect 2 saddle points in the approximation of the localization computation. And indeed, when you do the localization computation on the conformal boundary, which remember is the circle times the Riemann surface, you do find 2 saddle points that differ by a phase. And it corresponds perfectly with the actions of the black holes. So we are starting to see something inside the structure of the sum of the semi-classical approximation to the quantum gravity path integral. Okay, so I think I'm already almost over time, so let me summarize and conclude. So we found an expression for the on-shell action of all the smooth supersymmetric solutions of the simplest theory of gravity in 4 dimensions. And it was given only in terms of topological data, topological or geometrical data from the fixed point sets of a specific Killing vector that was constructed out of supersymmetry. We also showed that this property of localization in geometric sense also extends to the first higher derivative corrections, and also extends if you add a theta term to the action. This theta term necessarily doesn't appear if you consider Sasaki-Einstein, but it necessarily appears in this particular construction, which is very interesting from the physics viewpoint, because it's related to these mysterious 6-dimensional field theories. It holds in all the examples checked, of course, and it provides an expectation for the large n limit of the partition function of these CFTs. Most of the cases that I talked about are not known from field theory. So what can we do now? So at the very abstract and very conceptual level, research plan level, the question is why is this the case? Why do we have this index theorem like formula? Is there an actual index theorem that applies in gravity? And there has been some steps done by Ristov towards this direction. And also, what is the dual picture in field theory? So in gravity, we showed that there is a Killing vector that localizes that has fixed point sets, and the action can only be interpreted in terms of fixed point sets. These are fixed point sets in the bulk, in the 4-dimensional space. What happens in 3 dimensions? More concretely, so these are very broad and very vague questions. More concretely, one can consider 4-dimensional action where we add some scalars, and that makes the game more complicated. And also we can do large analysis of various field theories on different 3-dimensional manifold and check whether the formula is actually correct with more examples. And we can also check in some sense what happens to the subdominant contribution. There are field theory methods that allow you to look at the subleading contribution. So the corrections to the large n computations. These have been developed by Tolder and Willett. And with this, I conclude. Thank you very much for your attention and the questions.
Thank you very much.
Well, thank you very much, Pietro, for this nice talk. So I saw that there have been quite a lot of questions. So are there any more questions for Pietro?
I have one more question. Sorry, the 2 previous we have. Can you go back one more, please? One more. Next one. Yes, here. This partition function corresponds to the same black hole, right? As I understand.
Yes. So this partition function, yes. So this is a case where you do have a black hole. So this is the gravitational. Okay. So here I'm considering the partition function of. Okay. So from the gravity viewpoint, I'm just considering the SUSY black holes. This is the analysis that I've done until now. In field theory, the black holes, so the black hole at the boundary have S1 times sigma g. because I'm embedding inside, okay. Then I embed in 11D on sigma 3 times S4, and I obtain this guess. This is the thing that I should match. So when I embed on this, this tells me that the field theory to be considered is the 6D mysterious theory, sometimes it's called theory X by some people, the 6D theory X on sigma 3. Okay, this theory goes to a 3D superconformal field theory called Tn sigma 3, because it only depends on sigma 3 because, as I said, there is a mysterious, mysterious, I mean, you can prove it, but it's an unexpected relation that it only depends on the topology of sigma 3. So that's why it only depends on this sigma 3. Now, you want to compute the partition function of Tn sigma 3 on S1 times sigma g. This is the thing, and then you need to consider the large n limit of this. So this is the object that you should compare with. This is a very non-trivial computation to do, and it's related to something called the Reidemaster torsion of an operator on S1 times sigma g, and it's related to counting of flat connections, and whatever these people managed to do this computation, kudos. And what they find is that when you take the large n limit of these operators, you find two saddle points that have this structure, and it matches perfectly with the gravity computation. Notice that the gravity computation was much easier. That's why the AdS CFT correspondence is so appealing, because it was a classical computation. There was no quantum. There was no computation of spectrum of operators, as I'm on too. It's a much easier computation in a sense. Does this answer your question?
Actually, it is quite technical, but as I now I understand this Q plus and Q minus corresponds to the charge of the black hole, so negative and positive, right?
Yes.
So it is somehow related to this chirality picture of this supersymmetry.
Yes. So the black holes with positive on the charge, the chirality of the spinor on the bolt corresponds to the charge of the black hole.
Okay. Thank you very much.
This is this you can check with Mathematica. It's just 10 minutes of computation. Any other questions?
Actually, I have one, but I can't ask technical questions because I have
no, of course.
compute this kind of problems. But okay, I think on the page 10, you said that we take R is equal to 0 and it's calls some chirality. Yes.
Yes. Yes.
I think, okay, we are just interested in the bosonic case. But in the fermionic case, chirality creates some symmetry breaking. But in the bosonic case, I'm not sure what is the effect of this chirality on this kind of system.
So there is not really any effect. So remember remember that I said that a supersymmetric solution is composed of a metric on a, well, okay, so it's a 4-dimensional spacetime, a metric on the 4-dimensional spacetime, a U1 gauge bundle on this spacetime, and also a spinor, okay, formally a spin bundle plus a section of this bundle that satisfies the generalized killing spinor equation that I had in this killing spinor equation. Okay, so this is a solution. G and A also have to satisfy some equations of motion. Okay, great. Now, out of these, I can construct a vector xi, which is given by, so proportional to where gamma star is gamma 5 in normal circumstances. So when is xi is equal to 0? Xi equals 0 if epsilon is 0. That's the trivial case. But also when epsilon is chiral. Because at epsilon chiral, the entire thing degenerates. It's a degenerate case. The entire structure collapses. So you can prove by doing some global analysis that epsilon can never vanish at a single point. However, epsilon can become chiral. Therefore, when xi equals 0 are the same as epsilon chiral. Notice that epsilon is not a dynamical field. There is no kinetic term for epsilon in the Lagrangian. So it's not a fermionic field that moves on my space. It's literally just an additional thing that appears on the space. So so this gives you it's just a label. The chirality of this epsilon becomes simply a label of the fixed point sets for xi. So it's very different from, you know, chirality confined symmetry breaking.
Thank you.
You're welcome.
Maybe I have one more question.
Sure.
It is about the infrared limit of this field theory that you presented at the end. So what are the main subtleties that are involved, I mean, from a mathematical point of view, in taking this infrared limit?
So, okay, that's a very good question. So let me tell you. So in 3 dimensions, you expect that most theories flow in the infrared to strongly coupled superconformal, if they were supersymmetric, to strongly coupled supersymmetric conformal field theories. Strongly interacting and non-trivially interacting. Okay. The difficulty, why it's so mysterious and why there are a few thousand papers on this subject, is in formulating a description of the infrared limit of this Tn sigma that is simply given in 3-dimensional language. So I told you, these are, you know, whatever. I told you, these are the CFT that appear at the IR limit of wrapped M5 branes on sigma 3. This is the same as saying that it's the IR limit of taking a 6-dimensional superconformal field theory and compactifying on sigma 3. Cool. These are just words that fill your mouth and your papers, but don't really have a concrete meaning. Like, you know, can you write a Lagrangian for them? Is that an IR limit of a Lagrangian? That's the hard bit. So these people, and also these, they proposed an equivalent, a 3D Lagrangian that flows in the infrared to Tn sigma 3. So it's just a three-dimensional description. So they basically told you, okay, so the 5 brain wrapped on sigma 3 flows to a fixed point that can also be described in terms of the fixed point of a product of a billion gauge groups with a specific superpotential in 3 dimensions. So now that's a much more concrete prediction, because now I have a Lagrangian, I can work with it. I know how to do perturbation theory, and I know how to work with it. So that's the subtlety. It's checking whether this prescription does work or not.
So they also got critical exponents of the infrared limits.
And these no. This is much less developed than that. I mean, I guess you can find these type of things from the partition function, but you know, now I told you what is the field theory. Then you need to compute the partition function and compute all these things. That's another problem again.
Okay, thanks.
All right.
Are there any other questions? Okay, so if not, we should thank again our speaker.
Thank you.
Thank you very much for the clear talk.
Thank you.
And just as a side remark, so we noticed that some people connected like a few minutes ago. So maybe we should stress later on that there has been like a change in summertime versus winter time. And so take this in mind for our next talk in 2 weeks.
Okay.
Thanks.
So thank you for all the attending, and I wish you a good day. Have a good day.
Thanks.
Thanks, Pietro.